Okay, thanks very much. Thanks for having me. I've really been enjoying the workshop. So going to try to talk about galaxies as tracers of the matter density field. It's a bit of a bait and switch. I'm showing pretty videos in the beginning, and then I'll just go to some, I don't know, fifth grade math for the rest of it or whatever. But at least this way you'll think I actually do something with my life. So what you're seeing on the left here is cosmological structure formation in the dark matter regime. And on the right, what you're seeing is the physics of star formation, actually on very small scale. So this is an individual molecular cloud where individual stars will form in this. And so what we like to do is be able to connect up these scales, which are quite large. We're talking about AU scales to smaller on the right, probably gigaparsecs that we need on the left. And so this is a very computationally intense problem. On the left, we just have gravity. On the right, we have lots of hydrodynamics. We heard about the Riemann hypothesis yesterday. Another millennium problem is the Navier-Stokes equation. So doing the right is a complicated business. So what you're seeing is accretion of gas onto these protostellar cores. Now you're starting to actually see protostellar jets as the accreted material is shot out by the magnetic field as the stars start to form. So the energy and the feedback from these forming stars have a significant effect on the galaxies that actually live around them. And they also have a significant effect on the matter because if you shake a gravitational potential, then you can actually change the dark matter properties of the center of these galaxies. Of course, maybe I should title the talk, why is this astrophysicist here? And should we ask him to leave, since this is mostly not stuff that you're thinking about, but I'll try to convince you this is actually worth thinking about on related to the topics of the workshop. Okay, so the other thing I like to do movie-wise is look at cosmic structure formation. What you'll see on the left is your typical view of this, where we do things in co-moving units. You take out the cosmological expansion. But I also have on the right the exact same bit of the universe, but now in physical units. So you can really see how structure formation proceeds in both at the same time. So one of these grid cells will actually be this at the end. So this is one co-moving unit over here at the end. All right. So we can start here very early, of course, and you see structure sort of growing in place over here. Here you barely even see anything happening. But of course, structure takes a long time to evolve, and the expansion is the drag on structure formation that would otherwise be an exponential instability. And so we'd like to understand the evolution from that initially very smooth distribution to what you're getting here towards the end of a much more clumpy non-Gaussian distribution of objects. We can simulate this very well. Okay, given a big enough computer and enough time, we can compute all the properties we need of the dark matter, assuming gravity only, right? Assuming no interactions among the dark matter particles. But it's still very hard to produce something like this, James Webb Space Telescope image. And so what we'd really like to understand is how do you actually get the galaxies from this picture overall? So to connect back up to the big picture, lambda CDM works really well. Has 6 parameters, 2 parameters that talk about the matter content, 2 parameters that talk about the power spectrum, and 2 that are related to the CMB. They're sort of nuisance parameters at this level. And this is the power spectrum of density fluctuations. Okay, you can see the linear matter power spectrum. That's the solid line, and the dotted is sort of nonlinear evolution. So you can sort of see the nonlinear scale coming in here. And I think one thing to point out is we're used to thinking about the Planck measurements as being our best probes of cosmology, but the Planck measurements completely go away where you have any kind of nonlinearities, right? So if we want to understand much of the universe here, we need to understand nonlinear scales. So there's this enormous range of scales here. We're thinking if dark matter is a standard WIMP, that the smallest, the sort of free streaming scale might be an Earth mass or so. And sort of the CMB is probing, K of 0.1 or so. Galaxies and clusters, we're up to maybe 10. Smallest dwarf galaxies we know about, maybe up to 50-ish. And we think the rest of these should be starless halos here. And most of this range, or much of this range, is completely unexplored physics. Okay, so I start out with the CMB, and I can say, what do we do for an n-body simulation? So we do the n-body simulation. You take this, the properties of this Gaussian random field that are implied by the observations, and you use linear theory to extrapolate it to some early enough time when linear theory is still valid. Okay, and these are just linear density fluctuations now that are consistent with this Gaussian random field. And linear theory is nice because it separates the density contrast into the spatial bit, which just grows in place, and some time evolution. So all you have is just growth with this growth factor, which is just some integral over the Hubble parameter. So I can then extrapolate this if I want, not just to redshift 127, but I could use linear theory to go all the way to redshift 0. That's normally what people do. And if I sort of flash back and forth between these two, you can see that the overdensity, let's say at the center here, looks the same in this as it does here. It just a little much more enhanced, right? So the density contrasts are growing in place. All right. Sadly, the universe does not believe in this. It actually does gravitational evolution. And so if you wanted to understand things, you need to understand the evolution of what ends up being a very non-Gaussian field, right? So the previous one is still Gaussian at redshift 0. This is completely non-Gaussian. But we would like to be able to avoid doing big n-body simulations all the time. They're very expensive. That state-of-the-art simulation I showed before that includes hydrodynamics might have taken 45 million CPU hours, okay, and probably 45 million grad student hours also. So this is a serious resource issue. So what you can do instead is try to figure out clever ways to get around this. And people have done this these models are even older than I am, hard to believe. So Press and Schechter in the 70s told us that basically the linear matter power spectrum contains information about the statistics of the nonlinear fluctuations. And they based this on this spherical collapse model of Gunn and Gott. So you basically take a small density contrast in the early universe, and you ask, how does that evolve under gravity? They didn't have the cosmological constant, so this is even easier. But it's just a one-dimensional equation here. R double dot goes like 1 over R squared, right? And then some dependence on the density contrast. So basically, at very early times, this shell expands with the cosmological expansion fully, and eventually it'll break away from that expansion. So as a function of time, initially we have the sort of R goes like t to the 2/3 if we're just matter dominated. And then this shell will, at some point, if the overdensity is high enough, it'll reach a maximum, some turnaround radius, and it'll recollapse. Okay, and so this is the spherical collapse model, and it's pretty straightforward to do. A little more tricky if you include cosmological constant, but still eminently doable. Okay, so the nice bit about this is you can map the linear theory density contrast to the actual density that this overdensity has in this spherical collapse model. So what the shell would look like. So we're thinking of a top hat density, something that has constant density out to a given radius r, and then vacuum boundary conditions essentially outside of that, and that just collapses. So at turnaround, linear theory says that this object has an overdensity of 1.06, okay? But in the spherical collapse model, it actually is larger. So already linear theory is doing poorly here, and that's not surprising because this is significantly, or it's close to 1, right? At collapse, when the shell hits the origin again, the linear theory prediction is 1.686, and the spherical collapse model, which isn't when it's at infinite density at the center, but says it virializes at half of the turnaround radius, says you have an overdensity of about 200. So this is nice because it allows us in one way to map the linear density field to the nonlinear one. Okay, but does it work? Well, so what you can do then is you just understand the linear density field in terms of integrals over the power spectrum. Okay, so you're looking at the RMS amplitude or the variance, and you're smoothing this density field over some mass scale, and that corresponds to the mass scale you have here. And so basically, this is a Gaussian random field, so it has a Gaussian distribution, right? So I'm looking at something here that has a width of 1.686. I could look at a couple of other masses, right? So in this case, I have a more sharply peaked Gaussian, so a narrower width. This corresponds to a larger mass, or a larger width. This corresponds to a smaller mass. Okay. And this model says everything will collapse when linear theory says you're at this critical density, 1.686. So you just integrate how much of the distribution is over here, okay? And that fraction of mass in the universe, it's contained in halos at least that massive, is equal to the probability that the density smoothed on that scale exceeds this critical density, okay? So this is the basic picture. Spherical collapse, and this ansatz that relates the fraction of collapse mass with the spherical collapse model. Okay, and if you want to do this at different times, you just change the width here. So at earlier times, this moves over this way, and less of the universe is in collapsed halos. Okay, great. So this basically says from the initial conditions, I have a power spectrum that gives me the RMS amplitude of mass fluctuations when I smooth that power spectrum on some mass scale m, or some equivalently some radius r. And then I can go ahead directly and get the number density of objects from just this variance or RMS amplitude and that threshold for collapse. You see that as a function of mass, this decreases to larger masses, and this is the hierarchical nature of structure formation. So there's higher variance on small scales. So small scales will collapse first. They're always ones that exceed this threshold first. And again, as we go to higher and higher redshift, this threshold just goes up and up. So at the present day, that defines some kind of characteristic mass scale that's just going nonlinear today, something like 10 to the 13 solar masses. It doesn't say that you don't have fluctuations that have collapsed here. They're just further out in the tail of the distribution, and they're therefore rarer. And so you can sort of measure that by asking how far away are you from this threshold. And this is often called the peak height. Okay, so everything in a Press-Schechter-like model is contained with this peak height. So variance and this density amplitude. And in essence, this works kind of remarkably well. You can actually get really good dark matter halo mass functions with some slight variations that agree very well with observations based on this. And they look something like this, okay? So they have some exponential cutoff and a power law at small scales. And this also, in some sense, gives us information about the 2-point statistics, not just the 1-point statistics. So we can use this model not only to count objects, we can ask how correlated they are with other objects of similar mass on large scales. So this has been basically the workhorse for a lot of people's research in terms of trying to understand dark matter halos, their evolution, and their connection to the matter density field. If you do this, then you can start to understand how halos are evolving over time. So these are predictions for a mass as a function of redshift, and these lines are constant cumulative number density. So if I ask, where do I have a number density of halos that's less than 1 per cubic gigaparsec? Well, this is the mass that would have at a given redshift. Okay, and the way to read this plot, I would say, is you can think about a survey in the low redshift universe, say DESI, something like that. It might survey co-moving gigaparsec or more, so it's sensitive to halos that are maybe up to this mass, 10 to 15 maybe in the low redshift universe. But if we care about early times, these rare fluctuations, we're in a regime where we have to look somewhere else, maybe JWST. Okay, and then we're looking at smaller volumes, maybe 10 to the minus 6 instead of 10 to the minus 9. And so we're looking at significantly lower masses here. Okay, so what is all this preamble about? Well, we want to be able to connect up how the galaxies grow within dark matter halos. So the power spectrum sets the abundance. That's this Press-Schechter or extensions to the Press-Schechter model. And then the maximum stellar mass in a halo is then set by the halo mass and some other cosmological parameters, the cosmic baryon fraction, right? So these are adiabatic initial conditions, so you have the same amount of baryons per dark matter everywhere. And so the maximum amount of baryons you have in a dark matter halo is given by this number. And you can't get more stars in a halo than you have cosmic allotment of baryons. So this is an upper limit to the number of stars you can form per unit dark matter. And so this can define an integrated star formation efficiency. You measure some kind of stellar mass. If you know what the halo mass is, this is the maximum. And so you have a maximum integrated star formation efficiency of 1. So this is Theoryland. I like to live there. Observers tell me everything is very complicated in the real world. So you have gas dynamics, there's star formation. That star formation injects energy and momentum into the surrounding gas, magnetic fields, a little bit of sprinkle in some magic. Okay, so all of the effects here have the net result that we expect this integrated star formation efficiency to be significantly less than 1 overall. That is, if you think of a galaxy's job as turning its cosmic allotment of gas into stars, it's really bad at its job. And that's not just true in a general sense, in an integrated sense, it's also true in a differential sense, instantaneously. If you define it in terms of the star formation rate relative to how many baryons are flowing onto a halo at any given time. So some small fraction of this we expect to be turning into stars. This is our sort of the redshift 0 world, where as a function of halo mass, the integrated efficiency has a peak at around the Milky Way mass scale of maybe 20%. Differentially, it's relatively similar peak, slightly higher. But again, you're not at 1 anywhere, and most places you're much less than 1. Yes?
There is no difference between the different, I mean, I know there is a difference, but you are not sensitive to starburst versus Milky Way.
Starburst versus what, sorry?
When you look at the star formation rate, so different galaxies have different types. So you are not sensitive to that. That's what I'm asking.
Yeah, so we're normally thinking of this as a sort of an average. And so sort of, there is a spread, and instantaneously you might convert a large, over shorter than a dynamical time, you might convert a lot of baryons into stars. But usually the small scale physics is a very different time scale than the large scale. The dynamical time is set by a tenth of the Hubble time. And the dynamical time for star formation is much shorter than that. The virial radius, the edge of the dark matter halo, is basically where the crossing time is a tenth of a Hubble time. So this sets the overall scale for the problem from the gravity side. Okay, so this brings us to JWST. This set the stage for our expectations. What should we expect to see at higher redshift? Well, if you integrate over an entire lifetime, we've barely formed anything in stars here. At earlier times, it should have been even less, potentially. So this is a very technical plot where I have time on the x-axis and stuff on the y-axis. I tried not to make an astronomer plot where more would be at the bottom. So I'm trying to keep it for a physics audience here where the axis go up. And so what people were expecting here, of course, well, these are the measurements pre-JWST. More stuff recently, less stuff earlier. Okay, and we expected this trend to continue, basically. So the reason you expect this to continue is it takes a while for gravitational instability to set in, and there's sort of a scale below which you don't form any galaxies. So this should start to fall off kind of almost exponentially. And instead of seeing less stuff as we went back in time, we saw almost constant amount of stuff. So what is stuff? Stuff here could be any number of things. It could be star formation, could be the number of galaxies, could be galaxy masses, could be number or masses of black holes. It could be star clusters. So all of these things are much more abundant and changing less with redshift as we go back in time than we expected pre-JWST. And the reason, again, we expected this to drop off is that we see in the local universe that star formation is inefficient. And so this is implying some kind of higher efficiency. Yeah.
So star formation, one of the reasons star formation is inefficient, like you mentioned on the last slide, is because of feedback. Right?
Yeah.
So, but I would expect like for a galaxy of comparable mass, if I do it at redshift of 10, that's going to be a much more tightly bound gravitational system compared to 10 to the 12 solar mass galaxy today. So I thought the feedback would be less successful in kicking stuff out, and then more stuff would eventually form stars.
Yeah, I will get to that in a little bit. That turns out to be an effect. The other effect, though, is that, of course, in primordial gas at very early times, there's no coolants effectively. You need to form molecular coolants. We don't have atomic line cooling. And so it's very hard to actually cool the gas down to form the stars at the earliest times also. So there's...
Redshift of 20, I agree with you. But
yeah.
Redshift of 20, the period temperatures are like, I mean, of like 10 to the 10, 10 to the 11 solar mass halos are high enough to start.
But the number densities are 0 of those at that time.
Why is that?
Just I can go back maybe. You know, at redshift 20, right? The number density is exceedingly low for those objects. So if you look at JWST, right, it's maybe observed typical volume of 10 to the 6 cubic megaparsecs. At redshift 20, that means there's, you know, one halo of 10 to the 9 solar masses in the entire volume that JWST is observed.
But by redshift of 10, which is also within redshift
of 10, yes, then things have changed, absolutely, yeah. Great, other questions? Okay, on with the stuff. Great, so so immediately there were some issues here, right? You probably saw these hyperbolic titles, you know, of shattering distance records. Astronomers are often challenged, so this is not too crazy. Could break cosmology, a little more okay, Big Bang didn't happen, now we're starting to get really out there, so I think we can all agree the Big Bang happened, here we are. But these were one of the big topics and remain this. These are these so-called little red dots. They're named that because they look like little red dots when you look at them. Astronomers are terrible at names, right? So you see a supernova, it went off in 1987. What do you call it? 1987A, supernova. So little red dots here. And these are so-called universe breakers, so huge systems that appear to be far larger than was presumed possible so early after the Big Bang. So what's the issue here? Again, these aren't real lookers, so the point isn't how beautiful they are. The point is, if you look at them as a function of their stellar mass relative to redshift, they kind of lie here, okay? And so the most massive is maybe close to 10 to the 11 solar masses. That may not be particularly meaningful unless you think that the Milky Way today is around a little less than 10 to the 11. The biggest galaxies we know today in terms of stars are 10 to the 12. So if we run simulations and we ask what did the Milky Way's biggest progenitor look like back then, thousands of times less massive. Okay? So again, we're seeing very quickly getting to very massive and evolved galaxies, it seems like. So one way that people quantified this is by asking how much stellar mass density you have in a given volume of space above a given mass in galaxy. Okay, and this is what people were expecting from HST results based on the Hubble Space Telescope. So redshift 8, redshift 9. Again, you can see this dropping substantially, right? So even just in a delta Z of 1, this is dropping by almost an order of magnitude in the expectations. That's that diminishing of stuff as you go back in early times. And these are the observations. So there's maybe 2 orders of magnitude at redshift 8 and significantly more at redshift 9 here. And so you can just play these games like we talked about a minute ago and just ask how many possible baryons are there in halos that could form a galaxy this massive. And this region is where there's actually more stars than baryons available in those galaxies, right? So assuming they've converted all their stars all their baryons into stars, you lie at this kind of line, and these galaxies are lying right at that limit, okay? This is that 10% line, which was the sort of maximal star formation efficiency we see in the low redshift universe today. So we're way off of that. So basically, this early excitement was that the high redshift galaxies imply an uncomfortably large star formation efficiency compared to well, either compared to what we expect or compared to what nature allows in a lambda CDM model. Okay. Remember, these lines are just coming from cosmology. They're straight from the power spectrum and understanding the abundance of dark matter halos. Okay, so the details have changed, I'd say. The masses are a little bit complicated to compute. Unfortunately, nature gives us galaxy luminosities. The luminosities are dominated by the young, hot, massive stars. The galaxy populations are dominated in terms of mass by the cooler, low mass stars that are completely invisible in those JWST images. So that's a challenge. But even today, basically, there's a paper by Harvard astronomer, so very reputable, okay, absolutely. Within the flat lambda CDM model, once cosmological parameters are marginalized over, the Fresco sample requires an epsilon, the star formation efficiency of more than 50%, okay? And so they're taking a different set of galaxies than was the original ones. But we're seeing, even with different samples at somewhat lower redshifts, we're still getting this. Yeah, please.
Sorry, I came late. So how do we know it's star formation efficiency rather than the halo or whatever just being much bigger? So there was just a lot more stuff there than you thought.
So the argument is that the cosmology sets the abundance of the halos. So if you have, given the initial matter power spectrum, that limits what you can get in terms of the halo. So if the halos are much bigger, the only way to get that is to change something about the structure formation.
Right. So another possibility though would be the halos or the disks or whatever it's fragmenting is bigger.
It can't be the disks, right? Well, I mean, so it could be, but then that has to also requires the bigger halos. So it requires a larger reservoir of baryons than the initial lambda CDM density field gives you.
Right. So it could be that there's something else on this, or it could be that the bigger.
Yeah, so it could be, but it's got to get more baryons in somehow than you would have thought was possible before.
So as long as you have more baryons for whatever reason, yes. So we don't know for sure that star.
Yeah, if you could get some kind of large isocurvature mode, something like that, in certain parts, that would work probably. I'll talk about other bits as well. Yeah.
We observe the luminosity, but I thought a lot of these little red dots are quasars and not galaxies. So this.
So yeah, again, these Fresco ones are
confirmed,
like definitive. There's samples at lower redshift that are quiescent galaxies, no AGN activity at all, no star formation. They actually are just red and dead, and you can observe them spectroscopically. You can look really carefully at them. Sorry? They have these out to about redshift 5 or 6 now. The most extreme ones, I think, are redshift 3 to 5 that they've discovered. They're actually hard to figure out some of these out. You need different filters and everything to get these. But yes, it's true that the little red dots, some fraction of them could be actually, the luminosity could be coming from AGN. We actually have there are other models, but we don't know 100% what the light is coming from. That's right. And all this is the conversion of the light into the mass. But for the quiescent galaxies, that's not an issue. And so that's sort of part of the motivation for talking about this. So the details are different. The big picture, I think, remains that we require high star formation efficiencies in some places. So.
For these redshifts around like 6 or 8, like these samples were not observed by HST, for example, at all, or any of the previous surveys?
Well, some of these have been observed with other surveys and other instruments, but now with the sort of it's competitive to get observing time on these, and you to sort of get a spectrum of a redshift 5 galaxy, you have to have a reason to want to spend 20 hours to stare at it or something, and this was good motivation for a lot of people. And also, JWST has the filters that you need to do some of this in the longer infrared wavelengths for this. But lots of these are in HST samples. They're much more uncertain in terms of their spectral energy distributions or their spectroscopic properties. Okay, so one possibility is that we just change the cosmology, right? So for example, generically models that modify the early universe cosmology to solve the Hubble tension. I want to push the Hubble constant up. Okay, and in order to do that, to actually fit the observations of the CMB, you have to do something that basically increases the matter density a little bit, but more importantly, you change the spectral slope. So you actually have more power on galaxy scales relative to galaxy cluster or CMB scales. And so that means galaxies form earlier. So this plot is showing, as a function of halo mass, the number density of galaxies in early dark energy, which is just you should think of this as a generic early time solution of the Hubble tension, okay, relative to the standard Planck calculation. So a low redshift, it's very similar. There's an offset from 1 because they have a different Hubble parameter. If you plotted this in terms of NH cubed, it would be the same. So here, not very different. Redshift 3, you're starting to get significant difference. Redshift 15, right, we've got something like 10 to 20 times more galaxies at a given mass, and that allows you to start to be able to build these things more efficiently. Okay. Yeah, Lisa.
So the energy right is only like 10%, right?
Yeah.
And why is that giving you such a dramatic?
Yeah, so the abundance of these things is exponentially sensitive to where you are. You're on the exponential tail of a distribution, right? And so you're sort of changing sigma a little bit, but you're changing the number density by E to something like that. So the power of exponentials, yes. Good, okay. So, and the one way to probe this, the sort of original surveys are probing maybe 10 to the 5 cubic megaparsec, so volume densities of 10 to the minus 5 per cubic megaparsec. That's the stars here. If you go to larger surveys, you can get a factor of 2 more of these things, and that would really confirm these out of the Poisson noise limit that you want. And I also want to note that the enhanced early structure formation in these early dark energy models can be differentiated from just an overall enhancement in the star formation efficiency because the galaxies are less clustered in this case because they actually don't have to form as rare a halo. Okay, so if you can do clustering measurements, you can really start to differentiate here. So not just 1-point statistics. Again, the 2-point statistics will really help you. Okay. Let's just say, though, that it's not cosmology. I would love if it was cosmology. It'd be very interesting. But I think it's also interesting to consider what can we do in the standard cosmology with galaxies. So how can we get an enhanced early star formation efficiency here? If you talk to galactic astronomers, they're always saying the problem isn't why is star formation so efficient in early times, it's why is star formation so inefficient in the Milky Way. If you look at the Milky Way, they measure the molecular gas mass, and they say, okay, if you convert most of that gas into stars on a free fall time, the Milky Way should have a booming star formation rate of hundreds of solar masses per year. We don't see that. So molecular clouds are terrible. Even on a molecular cloud scale, they're terrible at converting gas into stars. And so what you see here are simulations of the star formation efficiency in a molecular cloud, where now we're looking at different cloud surface densities, okay? So mass per unit area. And at low surface density, something like, again, 10% of the mass is converted into stars by the end. But as you go up to very high surface densities of gas, you convert much more of the gas into stars. So what's going on here? Star formation efficiency depends on gas surface density in the low redshift universe. This always confused me substantially because these are not disks, they're actually balls. So why should it depend on a surface density, not a volume density? But I'm slow. So why? Well, dimensionally, surface density is basically just an acceleration. Okay, and so when you're measuring surface density, you're really measuring the gravitational acceleration of those clouds. And star formation is just a competition of the gravitational acceleration of the matter inward and the outward input of energy and momentum from stellar feedback. So you're just fighting back and forth here, right? And stellar feedback, if you have a standard IMF, just puts in a constant number in a young stellar population. The momentum injection rate is just a number, okay? And for those who worry about such things, this is very close to the Mond scale that people talk about. And so you can actually get Mond phenomenology explained by this. But That's an entirely different talk that I'm not prepared to give. Okay. Either here or to Mon people, especially to Mon people. Okay. Right. So we have a number here. And so this basically gives us an idea that we expect inefficient star formation if the acceleration is much lower than this momentum injection rate from stars. But we get efficient star formation if the inward acceleration from gravity is much higher than momentum injection rate. So that's why high surface density clouds are very efficient at converting gas into stars. Okay. And this suggests a characteristic surface density that separates these regimes. It's just set by the stellar feedback. Yeah.
Is disk surface density a good proxy for this surface density as well?
Sorry, which surface?
Is the galactic disk surface density a good proxy?
No, not at all. This is very local surface density, so you have to have the gas surface density in the cloud itself. Yeah. No, good question. Okay, so then you can ask, where do we find these high surface densities? And at low redshift, the only place you ever get this is in dense baryonic cores like molecular clouds. So I thought, okay, let me look at what a dark matter halo would look like. What's the surface density or the acceleration that's implied there? We have NFW as the form. It goes like 1 over r in the center. So that means the acceleration profile is flat in the very center. Okay, and so this is what it looks like. And I'm just normalizing to the acceleration at the virial radius. And so at the virial radius, you're at less than 100th of the critical density here. And in the very center, you're still even less than a 10th of this critical mass. So in the Milky Way, you never reach, even with dark matter, some sort of gravitational acceleration that might be able to confine stellar feedback. And you might say, well, what if I go to some very extreme concentration? 20 is sort of 2 or 3 sigma out in the concentration distribution. Still, you're well below this critical surface density. But the beautiful thing about high redshift, as we heard, right, is that everything's smaller. So the virial radius is smaller by a factor of 1 plus z at a fixed virial mass. And so the surface density is 1 plus z squared higher. So at redshift 9, you're a factor of 100 higher in surface density just from the dark matter that you have, right? So now, actually, at the edge of the dark matter halo, you're sort of close to this critical surface density. In the center, you're exceeding it. This is for a 10 to the 12 solar mass halo at redshift 10. Okay, and then you might ask also sort of what is the mass that's contained above this sort of critical surface density. And so something like 50% of the mass in the halo would be above that surface density. So that's a lot of mass where you could sort of form baryons efficiently into stars. We can look at this as a function of different masses, so different mass halos. You can see 10 to the 8 solar mass halos. This is roughly the atomic cooling limit. They're well below this critical surface density. 10 to the 9 still below, 10 to the 10 maybe starting to get there, but we're really talking about like 3 lonely dark matter particles, you know, so 3 GeV worth of, I don't know, maybe a TeV worth of dark matter particles here. That's not a star, right? But as you get to 10 to the 11, 10 to the 12 solar masses, you're starting to get a significant amount of the mass above this critical surface density. So then the real question becomes, how do you connect this to the halo abundance? Will you ever see something like this in the actual universe? So these are those same curves of how a constant cumulative co-moving number density of halos evolves with redshift. So these are very common objects. These are very rare objects. And if you put these curves on, they look something like this. They actually follow pretty well these constant cumulative co-moving number densities of objects. So at a fixed virial mass, you're going like 1 plus z to the 6th power here. And so this is where that critical threshold appears. That's where one particle in the dark matter halo at the very, very center is above this density. Okay, so you sort of want to be significantly above this. This follows roughly the 10 to the minus 4 number density sample. So the picture would be that if you can get maybe to here or above, so it's 10 to the minus 5, 10 to the minus 6, minus 7, these halos should all be in the regime where the confining potential in the center might be enough to overcome feedback. Feedback would be inefficient just because of the gravity from dark matter that's there potentially. So the picture might be in the a detailed simulation I ran. So puffy little clouds, Bob Ross style. 2% of the gas is converted into stars in this shallow gravitational potential well. But if you have a much deeper gravitational potential well, this can confine the feedback because the feedback is just set by the stellar processes. It doesn't know about the dark matter originally, right? And this potential is much deeper, and then maybe you're able to form in whatever cloud here, some 50% of the gas could be converted into stars. And if you do a model like this, you actually predict sort of stellar masses in dark matter halos of number densities that are relevant for the surveys that have been done that are pretty comparable to the actual observations. Notice I haven't put error bars on here because no one really knows what the stellar masses are to anything better than a factor of, I'd maybe even say 10, but certainly 5, right? So these points can move around a bit, but these are very consistent with having these dark matter halos that have a number density of 10 to the minus 6 per cubic megaparsec. The other nice thing here is that this explains why this falls off like a rock at low redshift. So these are 10 to the minus 4, 5, 6, 7 number densities. They basically evolve in the same way as the critical acceleration, and then they just fall below because the surface density is dropping or the density of the universe is dropping there. Maybe this would even give you something at very early times. You sort of have a baryon mass that's comparable to globular clusters in the lowest mass halos at the earliest times. So this is maybe a way to get seeds for black holes, direct collapse, maybe globular clusters, very speculative. But one point I want to make is that this is all assuming NFW, right? NFW has this constant acceleration in the center because you have a 1 over R cusp. If you change the dark matter microphysics, you can change what happens. Self-interactions could turn into a core. That core could collapse. Core could core collapse, yeah. So you might change this where it would start to turn down, might turn up, and this will change the implied efficiencies. So there is a connection to the dark matter physics directly here. Okay, so I think the place to really look for this is actually in cosmological simulations. So sadly, I had to run some of these. Well, actually, I didn't run. It's sort of like Mark was saying, like the students can do it all. I'm lucky if I can figure out my password. So this is Jenna Samuel is a fantastic postdoc. She's doing this enormous simulation. Normally, you do either a very large volume or you at sort of poor physics, I'd say, or you do a very small volume with rich physics. And the goal here is to do sort of the combination of both. So the entire volume has a resolved interstellar medium, and we can truly start to see the formation of stars and galaxies here. So what do things look like? This is the surface density of the galaxies here in the stars. This shows you a map of the ages, and this shows you what you see in JWST. Okay, so JWST images, if this is anything like reality, look very degraded compared to what you're seeing here, right? There's tons of these tiny star clusters that are forming here. Everything is very rich in these clusters, which are likely, some of them, to be progenitors of the globular clusters we see around us today. Okay, so again, the view that you have JWST is not one of sort of great detail. I mean, it's kind of amazing we're seeing something that's whatever 30 gigaparsecs away, so it's amazing you can see it at all, but regardless. Right, you go to the smallest galaxies, you really just do see dots. Okay, I don't think these are little red dots, but just to show you, the smallest galaxies are basically featureless. You can do some fun stuff with this. You can ask how well does this sort of spherical collapse model or things like that do for this. You can ask how the mass is assembling. This shows you radii that contain constant mass values. So this is 10 to the 11 solar masses of dark matter, 10 to the 10 to the 10, 10 to the 9, 8. And you can see this shell has reached a maximum. It turns around. it collapses and it sort of virializes at some kind of radius here. And so this sort of shows you the distribution and sort of when this dark matter halo actually kind of forms. Okay, so it's forming at redshift 12-ish. You can do the same for gas, and you see something very different. Right? The gas is shaking around a lot because you're seeing star formation. The star formation is pushing the gas out. The dark matter isn't moving nearly as much with this. And so the gas is shaking around substantially. So you're seeing basically these bursts of star formation in the Lagrangian shells of gas density here. So in the last couple of minutes, I thought I'd put myself out on a limb and talk about work in progress. And that comes back to the original part. How do we map the linear matter power spectrum, the linear density field, to the nonlinear density field we have today? I told you Press-Schechter. I sold you on that, said we can make great predictions here. It's a great idea. It doesn't really work in detail, right? So this is the Press-Schechter mass function in solid. These are simulation points, okay? So people have come up with clever ways to do better than the original Press-Schechter. Remember, the original Press-Schechter just has a spherical collapse model and the mass variance of the density field smoothed on some scale, mass scale. Here, you're basically seeing the same thing, only either with an ellipsoidal collapse, that's the Schatten-Torman model, or you're seeing in the dotted, I think this is just basically something that has some free parameters and fits it. So it looks effectively like the Press-Schechter or Schatten-Torman model, but they allow the parameters to be free. So it's not a sort of a first principles bit. But if we go back to this, remember Press-Schechter was 1974. We still feel very strongly that the initial density field is Gaussian to a very good approximation. So its statistical properties are completely specified by the correlation function or the power spectrum and derivatives. And so there's this famous paper that was then 40 years ago now, BBKS, where they did a full calculation of the statistics of the peaks of the linear density field, right? So this depends on the height of the peak in the field and its curvature, right? So these are local maxima. So there's the first derivative vanishes, and the second derivative has to be negative. And then there's some kind of covariance here between the two. So that's all you care about. All right, and with that, you can compute the number density of peaks as a function of the peak height. So that's the central value of the density, and the peak curvature x. So these are just in some special units where you're looking at the peak height relative to the RMS amplitude of the density field. The peak curvature is in units of a different weight of the power spectrum. And these look like exponentials again. Okay, but the point is you can do all these integrals. There's no problem. And the other point is this contains more information than Press-Schechter because Press-Schechter only contains this term, right? Yeah.
Are you taking the grad square? What is it with respect to, like mass or something, or the window or averaging, or sorry?
No, this is just you're sort of thinking got 3 dimensions, and I'm taking actually a gradient. These are radial gradient of the density field from a point that is a maximum in the local maximum in the density field. Yeah. So there's more information, right? You've done 2 different weights now of the power spectrum than you did before. The sigma 2, which goes like k squared relative to the RMS amplitude, and the sigma 1, which goes like k relative to that. Okay, so what does this do for you? So I'm trying to actually do these calculations now, and you actually get something that looks quite good with a pure spherical collapse in this BBKS density field. Okay, that's the data points. The dotted is the Schatten-Torman mass function. This solid is a mass function from, you know about the Millennium simulations, the hyper-Millennium simulation. It's gotten extremely big, 2,500 megaparsecs on the side here. So things look really good in the exponential regime. Looks less good here, you might say. But remember, these are peaks in the density field. They're not independent objects. So I think this is actually including sub-peaks within individual ones. This is the famous kind of cloud and cloud problem that Press-Schechter had. So if I want to compute individual halos, I still have to figure that out. But I think this actually tells you all of the things that could be forming galaxies, which is relevant also, right? Press-Schechter doesn't give you a way of doing that exactly. And again, the same model actually works quite well out to higher and higher redshift. In fact, it does better and better because you're more and more in the exponential regime here. So the hope is that since BBKS is a very powerful way of understanding correlations in Gaussian random fields, if you can use that same machinery and apply it to spherical collapse models, that maybe you can do a lot of things like compute correlation functions, other things in the nonlinear regime that you can't do with extended Press-Schechter models. Yeah, so takeaway messages, we still got a lot to learn about lambda CDM. Nonlinear objects are interesting, not just as tracers of the density field, but in their own right. And these simple models that relate the nonlinear objects to the linear density field are, I would say, surprisingly effective. It's a miracle that Press-Schechter works at all, right? At low redshift, galaxy formation is highly inefficient. Exactly how inefficient is important for understanding counts of galaxies around the Milky Way, for example, which can constrain the power spectrum and dark matter microphysics. I promised I'd talk about that in my abstract, so there it is. It's one sentence in the conclusion. Okay, good. At high redshift, galaxy formation is surprisingly efficient, and the challenge is to explain this along with that low redshift inefficiency. And so, is that what's explaining these little red dots, or is it just AGN activity? Is this dark matter model that I talked about responsible for the efficient high redshift galaxy formation? I think it's a simple explanation, but we've got to test it in detail. Maybe this is an indication of some deviation from lambda CDM. That would be very exciting. Something I didn't talk about is, if we want to deviate from lambda CDM, we have to be consistent with other observations. All those models that change early time physics reduce the age of the universe to below 13 billion years. And so then star clusters can start to be constraining again on the age of the universe. So we think we can get close to ruling out those models in general by measuring the ages of globular clusters nearby. And can I finish a paper on my own? Probably not, but we'll see. So yeah, galaxies can be more than just tracers in your cosmological analysis. So love your galaxies. Takeaway. Yeah, thank you.
Very, very nice talk. So we have questions. Other question from Mike?
I just have a very basic question. When you're calling galaxy, I think I would be calling star, right? So you can imagine like things to pull and more like a black disk that's not lumped together. Do you mean star?
Yeah, I think basically we typically would mean you need stars to be in a galaxy, right? It wouldn't just be a condensation of gas that has not formed into stars.
Still be a dense, you could still have like dense region of gas.
Then you have to have some reason it doesn't form stars, right? Once you, yeah, but if you can do that, that would not be a galaxy in this kind of picture, yeah.
Okay.
Yeah, I could imagine you have models that would do that, yeah.
But just if you were in this regime where star formation is not efficient, you're going to be left with gas, right?
Well, but you'd have some stars, right? Once the gas gets dense, it's not like no stars form. You'd form 1 to 2% of that gas turning into stars per. Yeah, so some smattering of stars that are there. Yeah.
Yeah. So would you say that this problem about the higher UV luminosity function is solved by taking into account the enhanced potential that's enhancing your star formation rate?
Yeah. So the UV luminosity functions don't seem impossible to match. People are getting those reasonably well, but again, it's implying these higher conversion efficiencies or a changing stellar initial mass function. So if you have a mass function that's more heavily weighted towards massive stars, then you get more light per unit mass. And so converting that light back into mass, you actually have over-converted, and now you need to actually say these things are lower in stellar mass. Confusingly enough, the evidence that's out there is that the everything goes in the other direction, that there's more low mass stars than you would have expected, not fewer low mass stars. But it's a tough game to play, this IMF business. And once you can change the IMF, you can do anything in astrophysics. Okay, that's the magic, basically.